think we're going to get started. So thank you all for coming to this week's Compass lecture. I'm here to introduce our speaker, Harry Levine. He started as an assistant professor here at Cal in July of 2025, so very recently. He's brand new here. He received his undergraduate degree from Stanford and his graduate degree from Harvard. Sorry. Where he helped develop a new platform for controlling arrays of atoms for quantum computing. After graduating, he joined Amazon for 4 years to work as an industry research scientist in quantum computing and quantum error correction. And now he's starting a new lab here at Berkeley focusing on quantum science with arrays of atoms. And I'm sure he's going to talk a lot about that. So let's welcome our speaker.
Okay, so yes, I will talk about arrays of atoms and how you can use arrays of atoms to build quantum computers. Please interrupt me with questions. That will make it much more fun for me, so feel free to jump in. Okay, so the context for this moment in the field, I want to give a little bit of like general thought about it because it's changing very rapidly and it's becoming a very important new technology. So quantum mechanics, this is very general. Raise your hand if you've taken quantum mechanics. Okay, sounds good. So quantum mechanics is like an extremely important theory in physics that describes the way the world works. It emerged about 100 years ago from certain observations that people made that nobody knew how to explain. Those observations were things like you illuminate atoms and then you look at the color that the atoms fluoresce, and they happen to have this very discrete structure where the atoms only emit very, very specific colors. And that nobody had any clue how to explain. People also had these observations that you shine light on like a metal and you get discrete numbers of electrons coming off. And nobody knew how to explain that with the descriptions that we had in physics for the world at the time. That was what we called classical physics. And so this field of quantum mechanics emerged to help us understand and explain all of the observations that were at the time unexplainable. And it's been an enormously successful theory, both in terms of now being able to understand in exquisite detail all of these phenomena, but also now to power our understanding of a lot more complex phenomena that we didn't really know at all how to think about at the time. And that includes things like really how atoms work at a very deep level, how astronomical bodies work, like neutron stars. You need to know quantum mechanics to explain how they work, as well as like materials and semiconductors and modern electronics. All of them require an understanding of quantum mechanics. Okay, that's not really what I'm talking about today. What I'm talking about today is what's been sometimes termed like quantum 2.0 or like a new revolution in quantum mechanics. And this is not really about using quantum mechanics to explain the world we see around us, which has been very successful, but it's more about looking at this theory and noticing that there's some very, very weird exotic predictions that it makes and trying to see, can we uncover those very specific strange things in the lab and maybe use them for something new? So an example of the types of predictions in quantum mechanics are things like superposition, where particles can be in two places at the same time. This is a little bit of a hand-wavy way to describe it, but it's kind of true. You can have like particles in two states at the same time, or you can have this famous thought experiment of a cat. This is Schrodinger's cat that could be dead and alive at the same time. Those are the types of things that quantum mechanics says should be possible. We don't see them in regular life, but quantum mechanics says it should be possible. Quantum mechanics also talks about, or has as part of the theory, this concept of entanglement, which is that two particles that you have in your lab or something, normally you'd always be able to say this particle is in this specific state and this particle is in this specific state. Quantum mechanics has a framework in which you can, the particles can be entangled such that there's no way to describe them separately. You can only describe them as one collective object. I'm waving my hands quite a lot here. What I really want to say is that these are very strange phenomena that usually do not occur naturally in the world. And what has become possible in very recent years is to try to elucidate these phenomena and explore them and control them in the lab. And that's a very exciting new frontier of physics because it's only in the last like 15 or 20 years that people have been able to explore this part of quantum mechanics experimentally. And so it's like totally new kind of branch of physics. This has emerged in recent years, particularly in an exciting way because people have figured out not only that this is a very new part of physics to explore, but that it could be extremely useful broadly for science and technology. And so examples of that are people know how to build or have at least a concept of how you might build quantum computers out of these principles like entanglement and superposition. These are new types of computers that should be able to solve certain math problems way more efficiently than normal computers. So that's a crazy thing. Like these ingredients of quantum mechanics could allow you to build a computer that can efficiently solve problems you wouldn't otherwise be able to solve. And it's also been understood that these quantum systems can do a lot of other things. They are now essentially forming the world's best clocks, which is a field called metrology. It's understood that they could be useful for secure communication that's like guaranteed by the laws of quantum mechanics. So like these are very exotic features of quantum mechanics, and now it's becoming clear that we could try to build new technology out of it. And so that has motivated now a very broad global effort. It's really originated in academia over the last couple of decades, but now lots of industry groups and involved in this as well. And quantum computing here really is like one of the main holy grails. There's so much reason to think that these computers could be extremely powerful and also extremely valuable if you could really make them. And so that is what the main talk is about today. Okay, any questions so far? Okay, so what does it look like to have a quantum computer in the lab? I'm going to tell you maybe a little bit later in more detail, like what things physically look like, but at a bit of an abstract level, what does it mean to have a quantum computer in the lab? What it means is that you have these things called qubits. So a qubit is an example of a quantum system that has two possible states it can be in, and it can be in either of those states or a superposition of those states. So it's an analog to a normal bit in a computer, which is like a 0 or a 1, and just encoding some information. A qubit is a 0, a 1, or a superposition of 0 and 1. So it's both at the same time. This is the quantum version of a bit. In addition to having just one qubit, you need lots of qubits. The more qubits you have, the more powerful a computation you could do in principle using these qubits. Just like with your normal computer, the more RAM that you have, the more information you can store. Or like the CPU gets more powerful as it has more and more bits that it can work with. So you need lots of qubits, and then you need to be able to control them at the kind of precise quantum way that we're thinking about. And so what that means, for example, is you should be able to initialize all of your qubits into some known state. You should be able to perform what are called single qubit gates. And a gate here means an operation that controls the state of a qubit, like it flips the state of a qubit. So a single qubit gate would be you take one qubit in 0 and you flip it to 1, for example. That would be like the gate that's equivalent to a normal computer that takes a 0 and flips to a 1. A single qubit gate for a quantum bit needs to be more powerful because it needs to be able to do things like make superposition states. So you take a qubit in 0, you put it in a superposition of 0 and 1, so it's in both at the same time. Not an obvious thing how to do. A light switch, you could think of like a qubit, it can be up or down at the same, or up or down, but it's not easy to put it in up and down at the same time. So you need a very special system that allows you to perform operations that create these very strange superposition states. You also need to be able to perform what are called 2-qubit gates. So these are operations on pairs of qubits. And the thing that you need to be able to do here is entangle pairs of qubits. Another thing that's really not obvious how to do, again, there's no analog for entanglement in normal computing and in the normal world. So this is a type of effect that you can only get when you have a deeply quantum system that is very well isolated, and when you have these objects that are able to interact in a controlled way to become entangled with each other. I'll give you a little more concrete sense of what I mean in a little bit. Lastly, you need to be able to look at your qubits and make measurements. So when you do a computation, you do a sequence of operations and then you measure the result. The sequence of operations are sometimes denoted in this kind of form. So if you take a quantum computing class, you'll see lots of diagrams that look like this, where you initialize a bunch of qubits, some of them in the state 0, for example. You do a sequence of gate operations. This is a 1 qubit, this is a 2 qubit, and in the end you measure. And in the measurement, we think of sometimes like taking a picture of the qubit and seeing, is it in 0 or 1? Okay, so this is the framework for how one thinks abstractly about quantum computing. Now, what I'm more interested in is how do we build systems like this? And that's a really hard thing to do because these effects are so subtle, they don't exist in the normal world, so we have to use new types of tools. And the types of tools that one needs in order to see and control these quantum effects revolve mainly around either cooling things down to very low temperatures or isolating things extremely well from everything else in the universe. So here's 2 of the flavors of those approaches. One of them is cooling things down to really low temperatures. So this is the type of approach that people take with a particular platform for quantum computing, a particular approach, which is based on what's called superconducting circuits. These are circuit components that people go and fabricate, and then they put them at the base of this very, very fancy refrigerator called a dilution fridge. This dilution fridge will cool your circuit down to fractions of a degree above absolute zero, like 10 millikelvin above absolute zero. So that's 100th of a degree Celsius above absolute zero. At this temperature, quantum effects become very prominent. And so superconductivity is one flavor of quantum effect that becomes really important. And you can use systems like this to cool your circuit and make a quantum computer out of your circuit. So there's a bunch of companies doing this. This is a picture of a particular circuit that was made by Google, which they call the Sycamore processor. I worked at Amazon and still collaborate with them. And we have our own at Amazon processors that look like this, also in a dilution refrigerator. So that's one of the types of approaches people can take to make quantum computers. The type of approach I'm going to talk about more today is based on atoms that are laser cooled. Okay, so what I mean by this is generally you have something like a vacuum chamber. And this is a picture of a vacuum chamber where there's a bunch of like stainless steel components that are bolted together. And then inside you have a bunch of air that all got pumped out. And so you're left with extremely low pressure inside this vacuum, which is what then allows you to have a very dilute gas of atoms in this vacuum that's left over. And those atoms now essentially are not in contact with anything else in the universe. And it's a starting point where you can then use lasers to cool the atoms and trap the atoms and manipulate them. So these atoms end up essentially being levitated in the middle of a vacuum chamber. And that's what allows you to isolate them and control their quantum properties. Okay, there's lots of other approaches too, which I won't really talk about. But ultimately, all of these approaches for quantum computing revolve around trying to isolate your quantum system from everything else in the universe so that these quantum effects can actually be controllable. Okay. Question? Yeah.
Why do you call it laser?
Why do we call it laser cooling? Well, we use lasers to cool the atoms down. Does that answer your question? Or what do you mean?
How do you do that?
Okay, great. That's on this slide even, I think, or on the next slide. Okay. But actually, I think it's before I tell you that. So the short answer is that lasers can cool atoms down. Normally, you think of lasers as only being able to heat things up. But it turns out that you can configure things right. I'll tell you that in a second. Yeah, is there another question?
Yeah, I'm curious how is kind of something clamp trap, or are those two different
That's a great question. So this framework is pretty similar to what ion traps look like. Ion traps are also made out of laser-cooled atoms. In the ion trap case, the atoms are ionized. They have one missing electron, so they're charged. That changes a little bit how you work with them, but you still laser cool them. You still levitate them in vacuum in the same kind of way. Yeah, and there's people here doing ion trapping, people here doing neutral atoms, people here doing superconducting circuits. So all these platforms are being developed by people here at Berkeley and all over the world. Yeah. Okay. All right, I'll come back to laser cooling in 1 second. Brief little concept about the structure of atoms, because that's super important to understand how we control them. So, right, so maybe some of you have taken quantum mechanics and maybe encountered like the structure of a hydrogen atom, where you learn that there's like an electron orbiting a nucleus, and it can't orbit in arbitrary ways. There are these discrete eigenstates, these discrete clouds of orbitals that are allowed for the electron around the nucleus. There's infinite numbers of them that consist of different like angular momenta for how the electron is orbiting, or different distance of orbit from the nucleus, like the electron can be orbiting at arbitrary distances. So there's all these different states. When we think about the structure of an atom and how we can control it, we often write down diagrams that look like this, where each of these horizontal lines is what we call one energy level of the atom. This is like a discrete state for an electron to be in around the atom. And they correspond to these different like wave functions, these different clouds that the electron can be in. The atoms have additional structure beyond just the ways that the electron can orbit. Atoms also have properties called spin. This is a very quantum mechanical property, and it emerges from even just a single electron. A single electron has this property called spin, where it can be like spinning up and spinning down at the same time. Or I guess I should say it can be spinning up or spinning down, and because it's quantum, if it's well isolated, it can also be in a superposition of both. So what we often have is all these different orbitals that the electrons can be in, but also different spin states for the electrons in the atom. And these are often good states in which we can encode a qubit. So an atom might have, for example, a lowest energy orbital state where the electron is pretty tightly bound to the nucleus. And that will be a long-lived state. The electron will stay there for a long time, but it has these two different spin states also. And so we can have those two spin states encode information. We can either encode the 0 in the spin down of the electron, or we can encode 1 in the spin up of the electron. And in principle, we can make superpositions of these, and they should live for long times because the spins are very well isolated. Okay, so this is the basic structure of the atom that's useful to have in your mind. And then how do we actually take advantage of the structure and do things? So we start with a vacuum. This is another picture of this vacuum chamber. And then what we do is we have a section of this vacuum, which is all glass. So there's a little section here that's kind of hard to see, but right inside here, there's what's called a glass cell, just a glass tube extending from the vacuum. The reason that's cool is because you can see right into the vacuum. You can even shine lasers into the vacuum. And generally the workhorse for how we control atomic systems is we use lasers. So we need a way to get the lasers into our vacuum. We have this glass section of it, and so we can shine lasers from all sides. And that's now the starting point for how we do laser cooling. So laser cooling relies on, well, there's actually, I should say, there's lots of types of laser cooling. There was multiple Nobel Prizes related to the technology here. One very famous one related to the oldest known technique for laser cooling, which is called Doppler cooling. The rough idea is you send lasers from all different directions into your atoms. And you tune the lasers so that if the atom is at a standstill, the lasers will just pass right through the atom. The lasers will not have the right frequency to excite the atom to a higher excited orbital. But you tune the lasers such that if the atom is moving towards any of the lasers, it will have a Doppler shift of it will see a Doppler shift of laser frequency, and then it will be able to absorb light from that laser. That light will essentially mean the atom is absorbing a photon and getting a momentum kick. So you can kind of picture the atom is in your vacuum and it's wandering around. It's like moving around. It's kind of hot, but in any direction it tries to move, it starts absorbing photons from the laser that's opposing it, and that slows it down. So you shine in lasers from all these different directions into your vacuum chamber, and you can essentially, using techniques just like this, cool atoms to extremely low temperatures in a levitated ensemble in your vacuum. Here's a picture I took actually on my phone when we first did this when I was a grad student. So this is a picture of probably about 1 million rubidium atoms that are being levitated and laser cooled in the middle of a vacuum chamber. And you can often see them by eye. In fact, a lot of the labs here at Berkeley, you could even go see clouds of atoms that are being laser cooled by eye. Okay. So to make a quantum computer, it's not so good to have millions of atoms that are all indistinguishable and all mixed together. We really want to isolate single atoms so we can control each single atom individually. And for that, yeah, question?
Sorry, going backward, you mean by eye, the frequency of the laser is like a wavelength you can see by eye, or is it just anything?
So when you're shining the laser on the atoms to cool them, the atoms are absorbing photons from the laser and they're re-emitting them in all directions. And so you can see this by eye as long as they're emitting enough photons to be bright enough and it's a color that you can actually see. So this was a color that's kind of barely visible by eye, but it was showed up on my phone. Other labs here, the atoms will be emitting blue light, and then it's very easy to see them. Does that answer your question? Okay, so the next tool that we really love is to not just have this cloud of atoms that we're laser cooling, but instead to be able to isolate single atoms. And to do that, we use these very amazing tools called optical tweezers. So an optical tweezer is a very tightly focused laser. And it's so tightly focused that at the focal spot, it can actually trap and isolate single atoms. Okay, I'm not really explaining how, but essentially, if you shine an optical tweezer into this cloud of atoms, you'll pick out single atoms. And we can do this not just with one optical tweezer, but with a whole array of optical tweezers. So we shine in an array of laser beams. Each one gets focused to a very small spot, and it picks out single atoms from this cloud of laser cooled atoms. So this is really like how you extract a quantum system that now you can control and see at a single particle level. These are single atoms. Like normally you never get to work with single atoms, and they're levitated in vacuum. So they're super well isolated from everything else in the universe. And that makes them a really fantastic quantum system in which you can study and try to control everything. Or in this case, try to build a quantum computer. a lot of these labs are based around all the lasers that you use to cool the atoms and take pictures of them and control their state. And so there's lots and lots of lasers that are all tuned to different frequencies in order to control the atoms. And so here's a very rough diagram. I'm not really going to explain in a huge amount of detail, just to give you a picture roughly of like all those different colors that are of lasers you have in the lab and what they're all doing. So this is an example of a specific level structure of all the different states of a rubidium atom. So I like to laser cool rubidium. That's my favorite atom, at least right now. Each person who laser cools a different atomic species will have in mind a different set of levels that they think about, because each atom is a little bit different, has a bit different structure. But this is the structure for rubidium. And if you want to do all these sequence of operations we said earlier, for example, first you have to cool the atoms. So you shine a laser at a specific wavelength that goes to this state. That's the laser that you shine from all these sides, and it cools the atoms to really low temperatures. Then you have to shine another laser that you focus to make this optical tweezer that traps the atoms. It turns out this laser, you pick a different color that's not quite resonant with any of the specific orbital transitions. Then you pick another laser that you use to initialize the atoms. Actually, you can use the same color. You pick another laser or microwaves that you can use to drive transitions between the two qubit states. You have another laser that you use to excite atoms to different states that allow them to get entangled with each other. So there's a whole assortment of lasers that you shine in. And for people that work with rubidium, they know all of these wavelengths by heart. For people that work with strontium, they know another set of wavelengths by heart. And each one is like a little bit of a special animal that you have to learn. Like, what are the best ways to get good lasers at 780 nanometers? And you like get to know this kind of thing. Okay, and then you also need to take pictures of the atoms. Generally, you use the same laser that you use to cool the atom, because when you're cooling the atom is emitting photons. It's absorbing and re-emitting. You can collect those photons on a camera and take pictures of the atoms. And I'll show you some pictures in a second. Okay. So I'm not going to quiz you on any of these wavelengths, but I'm just hoping to give you a sense that there's all these different tools that you need and all these different levels, states of the atom that you can manipulate and can help you control. All right. Before I show you some pictures of atoms, I want to tell you a little bit more about what it looks like to have not just one optical tweezer, but many optical tweezers. And one of the selling points of this type of approach for quantum computing is that it's relatively scalable. So starting with one laser, you can actually make huge numbers of optical tweezers that can each trap and control single atoms. So I want to just give you a little bit of like the tools of the trade for how people do this in the lab. And one of the most important tools is this quite amazing thing called the spatial light modulator. One thing I want to say about these tools, none of these tools were invented for atomic physics. None of them were invented for quantum computing. These tools were pretty much all invented for completely other purposes. And then atomic physicists have like found cool ways to use them to control the lasers in our labs. So like the spatial light modulator is actually adapted from the types of tools in this projector that take one light bulb and shape it into this very complicated pattern. So the way that we use it in atomic physics labs is we send one laser onto the spatial light modulator. And this spatial light modulator we can program on our computer in the same way that our computer is programming this thing. So by programming it in different ways, we can steer one laser around, or we can even split one laser into a bunch of different beams. So this is the amazing thing. One single laser combined with this programmable element that our computer controls can split the laser into tons of different beams. I'm showing you here a certain pattern. We focus all of these beams into our vacuum chamber where they form our optical tweezers. We can collect the light from the optical tweezers and take a picture of them. And this is an example picture of those tweezers themselves. So this is just a bunch of little bright spots of light. These are the lasers that are forming traps themselves. So you can imagine each of these bright spots is a little trap for a single atom. But now how do we get the atoms in there? Again, coming back to this laser cooling idea, we shine in lasers from all these different sides, and that allows us to create a cloud of cold atoms that is overlapped with these tweezers. And then that loads single atoms into the tweezers. Then we shine in more lasers to cause the atoms to emit photons that we can collect on a camera. And we get pictures like this. So these are pictures of single atoms. Each of these dark spots now is one atom that emitted a bunch of photons that were collected on our camera, so we can see exactly that one atom. Each time this image was updating, it was a different assortment of atoms. And that's because each time you do this experiment or this process from scratch, you don't load a tweezer deterministically. It turns out that there's like a probabilistic loading process where you only get a tweezer loaded about 50% of the time. So you get this random filling of individual atoms in your tweezers. And then you can use other tools. For example, there are tools where you can take one laser and dynamically move it around in space. And that would be like a tweezer that holds an atom that can move that atom around. And here's what that might look like. For example, if you want to load all these atoms randomly and then move them around into a deterministic pattern, you could take a picture, see where the atoms are, and then go in with these movable tweezers that pick up certain atoms and move them around and rearrange them into a target pattern. And then this is what you might see. You now have some kind of programmable deterministic arrangement of atoms. Okay. This is one example of a type of lab that does things like this. I picked this one because it's very fun to look at. Some of them are organized in different ways. This one looks very chaotic, but it's fairly representative nonetheless of the bulk of the work that goes on in atomic physics labs, which is you have all these different lasers. Each laser needs to be very carefully stabilized and then guided into your vacuum chamber. And so what you're seeing here is huge numbers of mirrors and lenses and polarization controls that are shaping your lasers so that when they shine into the vacuum, they control the atoms in exactly the right way. This is not to scare you at all. It's actually super fun to make things like this. It takes years. This is like the kind of thing that you might make over the course of a PhD. Okay. The real selling point is that you get to take beautiful pictures of atoms. So this is a picture of one of the largest tweezer arrays that anybody has made. This is from a group at Caltech, where they made not just like a few hundred single optical tweezers, they made 10,000 or 12,000 optical tweezers. They load them and they get a random loading pattern. But this is the random loading pattern, then they can then take a picture of all those atoms and see every single atom. These are cesium atoms. They're a bit different atomic species than rubidium, but have pretty similar behavior overall. So quite a remarkable thing. Like, again, you started with one laser, you split it into 12,000 beams just by programming on your computer exactly how you wanted to split it. And now you get 12,000 optical tweezers, each one with a single atom. Take a picture of all of the atoms at the same time. Here's another pretty picture. This is from another group. I'm just showing a couple slides of other groups. Soon I'll hope to be able to show pictures of atoms we have here at Berkeley, but we're not quite there yet. So this is another picture of about 10,000 atoms. Yeah.
There's a request to see you.
Oh, okay. Yeah, sounds good. Sorry, I veered off to this side. Here's another picture. It's a little bit less easy to resolve the position of the atoms, but these spots still here are really all single atoms. What's also very fun is that you can arrange the atoms however you want. So a lot of people enjoy making fun pictures of the atoms. So this is the Mona Lisa that was made by a group in France, arranging the atoms into a beautiful arrangement. This group also arranged atoms in the structure of the Eiffel Tower in 3 dimensions. Turns out you can also arrange atoms in 3D. Pretty amazing. You can also make movies of atoms. So this is a movie that I helped to make when I was a grad student. This was our Atomic Mario. And honestly, these kinds of like pictures get about as much response from people as the science that we do. So it's fun. Okay, here's a more practical example of what these modern systems look like, especially when people are getting to larger and larger scale. So this is a group also from Harvard where they're loading 3,000 single atoms, but they're doing it in this very repeatable and continuous way. So they have this new system where they can load a bunch of atoms and then load new atoms into the system rather than trying to load all at once. This is something people call continuous loading. And it's a pretty hot topic because when you have atoms in your system, they don't stay there forever. They actually get lost periodically. And if you want to sustain your operations for really long times, you need some way to bring fresh atoms into your system. And that's a new frontier that this group has now demonstrated. And again, you get beautiful pictures or movies now of atoms moving around to see how they behave. Okay. So how am I doing on time? Okay, great. So I hope I've given you like a little bit of an overview. You can load tons of single atoms into your optical tweezers. You can take pictures of them. So now again, coming back to this concept of how do you use them for computing? Well, we often visualize it in this formulation. So I'm kind of not showing the tweezers themselves anymore, but you have all of these atoms. They're all levitated in a vacuum. And all of the atoms, you can shine lasers onto those atoms to control their state. You can move the atoms around. You can take pictures of the atoms. And so those are the tools that you use to do the quantum computing. So again, like each of these atoms has these two states that roughly look like the spin state of an electron. Those states are what encode the qubit, and you can use lasers to prepare superpositions of these qubit states, or flip from 0 to 1, or measure the whether you're in 0 or 1. There's also these excited states called the Rydberg states. These are one of the states I showed you on this earlier diagram. It was the highest level state that I showed you. I didn't really tell you what it is about, but let me tell you briefly now. So Rydberg states are these electronic orbitals that are very highly excited in the atom. And what that means is that the electron normally is very weak, is very tightly bound to the nucleus, but these highly excited states, the electron is super weakly bound. So think about it like the orbit of Pluto relative to the sun versus the orbit of Mercury. So it's like very weakly bound state. What that also means is that the electron happens to live pretty far away from the nucleus. So the size of that electron orbital is actually way larger in these highly excited Rydberg states. That's a really useful thing. And the reason is because if you have two atoms that are near each other in their ground states, in their normal qubit states, they don't talk to each other at all. So they typically will live a few microns apart from each other. Like this kind of distance here is microns. Atoms in their normal states are tiny, tiny. They're sub-nanometer in size. So they're nanometer in size, microns apart. They don't talk to each other at all. But if you use the laser to excite those atoms to these Rydberg states, the electrons now can live like a micron, like a kind of micron scale orbital, or at least fraction of a micron. So two atoms that are near each other that were non-interacting, all of a sudden start to very strongly interact when they're in their Rydberg states. And that is exactly the type of interaction that can lead to entanglement in a controlled way. The rough idea kind of looks like you excite one atom to the Rydberg state, and now if it was excited to the Rydberg state, it will prevent the neighboring atom from being excited to the Rydberg state. That's something called the blockade. That is exactly the type of interaction that allows you to get the behavior of one atom to depend on the state of the other atom, which generates the type of entanglement you need for quantum computing. Yeah.
I remember the other day you were saying that to measure if it's in like the 0 state, shine a laser at if it was in one of those would it get excited.
Yeah.
Do you ever like run into a problem where you excite it, but then that upsets the one next to it somehow?
You mean the atom next to
Yeah.
it? Absolutely, you do. And that's one of the problems. That's one of the challenges people are trying to figure out how to handle. So if I want to take a picture, okay, if I want to control one atom without affecting the neighbor, my options usually are I have to focus my laser onto this one atom. There's a few things that are hard about that. One of them is that it's kind of hard to focus a laser so tightly onto this atom such that it has no overlap with the neighboring atom. You might worry that it's going to affect the neighboring atom too. Another consideration is if you're trying to focus your laser onto one atom to cause it to scatter photons so that you can take a picture of it, those photons absolutely can and will be absorbed by the neighboring atom. And if this neighboring atom is supposed to be in a superposition state, which is like this isolated quantum state that shouldn't, then it really should not absorb any of those photons. So you do worry a lot about that. In these systems, as I'll come back to in a second, a lot of the value is that you try to avoid needing to control one atom but not its neighbor. And it turns out in many cases, we're very happy to control lots of atoms in parallel, to do the same thing on all these atoms at the same time. So read out this atom, like take a picture of this atom, but also take a picture of the neighboring atom. And so that makes this process a little bit easier, but it still is often necessary to measure some of the atoms without the neighboring atoms. And so that requires some work. And I'll come back in 1 second to how people do that. Okay. Okay, so I was talking about Rydberg states. You excite the atom to the Rydberg state. Two atoms that are near each other that were non-interacting now are strongly interacting. They get entangled. And that's the type of operation that is this 2-qubit gate that you use in your quantum computer. Okay, so these neutral atom processors, we sometimes refer to them as quantum processors. They feature some things that are quite special, especially in contrast to other platforms for quantum computing, although I haven't talked at all about the other platforms. One of the things that's very special is that every single atom in a system like this is exactly the same. There's no like your rubidium atom is a little different than my rubidium atom. They're exactly the same. This is a crazy system to have in the lab where you know exactly the state of every single atom involved. What other system is like that? If you fabricate a very precise, like pure material, you're not going to know if there's like one defect atom. Like that's very hard to rule out. And in many cases, the presence of small defects in your system can really affect the behavior of a system. Here, you can know exactly what atoms are involved in your system, and they all are exactly the same. That also couples with the fact that these atoms, because they're so isolated and they're not near any defects, they're not near anything, they can stay in superposition states or they can remain entangled for very long coherence times. Coherence time here is defined roughly as if I put an atom in a superposition, how long does it stay in the superposition? Roughly speaking, that corresponds to how long does it take for anything else in the world to collapse the atom into being in one of the two states. So if you have a light switch and you try to put the light switch in a superposition, the light switch will not stay in the superposition for very long at all, because all this light is bouncing off the light switch and revealing, kind of collapsing it to show which of the two states it's in. But if you have an atom in a superposition of two different spin states, levitated in vacuum, it can stay in that superposition for seconds or minutes. So it can preserve those quantum effects for seconds or minutes. Another thing that we really love here, which I was just saying earlier, is all the atoms are the same. And in many cases in a quantum computer, you actually want to do the same operation on all the atoms in your system. So you shine one laser, illuminate all the atoms, and get them to evolve in the same way. And that couples very well with this other capability to move atoms around dynamically during a sequence of computations. And here's a picture of an early version of what that looked like. So what we have here is about 16 atoms that are stationary. They're just fixed in space. And we're looking at an example of how you could program a sequence of gate operations, where the gate operations roughly look like, I want to entangle this atom with 4 of the neighboring atoms in the system, or 4 of the other atoms in the system. So how do you do that? Well, you bring, in 4 sequential steps, you bring atoms close to certain neighbors, and then you hit all of the atoms with a laser pulse that entangles those atoms with their neighbors. That's being shown by these red circles. These red circles come up when you hit the whole system with a laser pulse that entangles all pairs of atoms that are next to each other. So you're programming a sequence of operations by laser pulse on the system, move atoms around, laser pulse on the system. This is one of the frameworks by which you can do quantum computing with atoms. There's a few others. You could also say, let's keep all the atoms fixed in place and control everything by laser pulses on single atoms. That's another model. And probably some combination of the two is like the future. Yeah.
When you say entangling, does that just mean that one state is tied to the other, or that after you move one of them away and change it, that changes the other?
Yeah, so you're asking, like, what does entanglement mean?
Basically.
Yeah. Entanglement is, I would say, a hard thing to explain. There are certain analogies. So one analogy is that if I have like a pair of shoes and I give you like you take the right shoe, I take the left shoe, or you take the left shoe, I take the right shoe. These shoes are correlated in the sense that I know that if I look at my shoe, I know what shoe you have. I know that you have the opposite parity shoe. So entanglement is a more complex version of that, and it's a little hard to explain exactly how it's more complex. The reason is because before I measure, like when we share these shoes, each of our shoes is in a very well-known state before we look at it. It's just that we have to look at it to learn that state. When you have entanglement and we share this entanglement, neither of our particles are in well-defined states before we measure. And it turns out that no matter how you measure it, no matter like which angle you look at it from, it's guaranteed by quantum mechanics that you will always find the opposite outcome. This is probably not the most helpful explanation. I wish I really had a better explanation, but this is kind of the special thing that makes quantum mechanics different. It has this concept of entanglement. It means that our objects are just not in well-defined states before we each measure it. Maybe I'll emphasize one point again about this. I think probably the most deep, like the most fundamental thing is without entanglement, every single thing can be described by what state is this particle in. This atom is in this state, this atom is in this state, this atom is in this state. That means that it's not hard to write down the state of my set of atoms. I can just say, okay, this atom is this state, this atom is this state, this atom is this state. If the atoms can be entangled, you cannot describe them as this atom is in this state, this atom is in this state. You have to instead say, these atoms are all in this combination of states. And there's a lot of combinations of states they can be in. And that's one way of seeing that entanglement can kind of encode information in a more complex way. Really hard question to answer. Similarly hard to how do quantum computers actually solve problems more efficiently? Also very hard question to answer. Okay. Any other questions? Yeah.
How many actual atoms are in like a logic?
I haven't talked at all about logical qubits. So let me come back to that. How about that? Okay. All right. So this is like an early version of a picture for what it looks like to program these atomic processors. You move atoms around, you entangle them in these programmable ways. A more advanced version now is to try to dedicate sections of atoms to doing different things. People call this a zoned architecture, but this is one flavor of strategy for how you might move atoms around and try to control them. And so one thing that addresses your question from earlier is that if I want to measure a section of atoms without disturbing the neighboring atoms that are right next to them, where I'm worried that my atoms are scattering photons that can be absorbed by my neighboring atoms, what you could do is move those atoms to a separate section of your processor where they're now kind of far away from the other atoms. Now you can take a picture of them. Even if they scatter photons, the neighbors that you were worried about are pretty far away, so they're not that likely to absorb. So this is a type of strategy. You have sections of qubits that you kind of control as big chunks, and I'm not really telling you at all what that means, but I'm just going to show you another cool movie that illustrates, again, the kind of concept. This is a more recent video that is a much more advanced demonstration of now this thing called quantum error correction, which you're asking about. I'll talk about that on the next slide. But roughly, it's just showing you different sections of atoms that can be processed and controlled in different ways. All of this is just like where the atoms are. There's also all these laser pulses hitting the atoms at various stages to do the gates, to take the pictures of atoms, to entangle them. Okay, so I'm going to come close to ending by alluding to this concept of error correction, which is that when you take qubits like the spin of an atom, or like the two states of an atom, we'd like to think that they're these perfect qubits. They're so well isolated. I've told you like 1,000 times how well isolated they are and how beautiful. But they're not perfect for storing quantum information. And quantum states are inherently quite fragile. So there are various mechanisms that cause errors in quantum computers. One of them is that if I put the atom in a superposition, I told you that it can stay in the superposition for seconds or minutes. That's amazing, but it's not infinite. And that can be a very significant source of errors in real quantum processors. And if you do advanced quantum computations, they often require very long sequences of gate operations and of like storage operations. And if any of those fail, you'll get the wrong answer in the end. So you have both problems of this so-called idle decoherence, which is just like errors that occur while you're trying to hold a qubit. There's also gate errors, like you're trying to entangle these two atoms and you can't do it perfectly. In fact, people typically can only entangle atoms with error rates at the level of like 0.1% or maybe a little bit better. So 0.1% gate error is pretty good by the perspective of like, it's a new part of physics to be able to see, but it's not good enough to do billions of operations and still get the correct answer. And so I'm going to just skip this. So what's quite remarkable here is that it was thought in the 90s that these problems were just insurmountable and that nobody would ever be able to build a quantum computer that could do useful computations because of these intrinsic fragility concepts in quantum computing. And absolutely remarkably, there was a new field invented called quantum error correction, which was a resolution to this. It was a way that you can take imperfect qubits, imperfect atoms, for example, that suffer errors, but collectively use them to encode quantum information or qubits redundantly. And that allows you to protect the system from errors. And that's through what are called logical qubits. So you take many different physical qubits like atoms that are all imperfect qubits that you can't control with 100% accuracy, but you use them to collectively encode one protected qubit's worth of information. And that protected qubit can have orders of magnitude lower error rates. It's super hard to do this. And this is really like a major frontier right now. Like in the last year, 5 groups have now shown like the first demonstration that this concept is starting to work. It's very preliminary in the sense that the logical qubits, this redundantly encoded qubit, is now just a little bit better than the original qubits. For a long time, the redundantly encoded qubits were worse than the original qubits, not helpful. Now they're barely a little bit better, but it's kind of at the point, it's at a tipping point where now small improvements of the systems and increases in the scale of the number of qubits will start to exponentially improve the performance of these logical qubits. So we're at this point now where it's looking like in the next some number of years, 5 or 10 years, people will be making logical qubits that have phenomenal performance, better than any qubit anybody could make otherwise in the lab. So absolutely remarkable, and it's a really important time in the field, like right now. So I just wanted to make sure to mention this. Okay, so I have, I think, 2 more minutes. And I'll just close by saying briefly like what we're doing in our new lab at Berkeley. We started 4 months ago or 3 months ago. And so we are working on, are there comment?
No,
So,
that's me.
great, okay. So we're working on systems like this. We're building up a new atomic physics lab. So we're building our vacuum chamber right now. We're setting up all the laser systems that we need to do all of this. We're hoping to take pictures of single atoms in some number of months, hopefully not too many. And what we're particularly going to work on is a couple of new ideas for how to control single atoms in a very precise way. And at least one of these aspects is related to the problem, again, that you brought up, which is what happens when I measure an atom? Does it kind of cause issues on the neighboring atoms? So we're going to pursue an idea for what we think could be a very fast version of a way to measure single atoms without it affecting neighbors. And it uses this very other exotic thing in quantum physics called squeezed light, which is something that people use at LIGO, if you've heard about gravitational wave detection. So I can tell you more about that if you're curious. We're also going to be working on good ways to efficiently control groups of qubits to do quantum error correction, as you said. And the other thing that I'm super excited about is not really quantum computing. Do you have a question? Okay. Not really quantum computing, but another concept related to controlling these like crazy exotic quantum properties of single atoms. And what we're going to try to do is take single atoms and split them into spatial superpositions so that we would have one atom in a superposition of being over here in this optical tweezer or over here in this optical tweezer. So it's another way to control the state of atoms. Today, I only talked about superpositions of like the spin of a single atom in place, but you can also make superpositions of the spatial position of atoms, like spatial wave functions. And so this is actually following in following the lead of Holger Mueller's group, which is atom interferometry, which is the field of physics that this fits into. And the last thing I'll say is physics should be fun. So especially if you're doing physics research, try to find a fun team. And here we are unboxing a very expensive vacuum part and going for a hike. And anyway, yeah, very happy to answer any more questions you have. So thanks.
Any questions for our speaker?
I'm wondering what platform for quantum computing sleeping involves successful or the goal in different in industry for decades, or do they will be probably like a combination of types of parts of
The question for Zoom.
Yeah, the question is, what will be the most successful quantum computing platform to be used in industry, and or will it be like a hybrid kind of quantum system? Is that the question? So I don't know that I will make a concrete bet. What I will say is there's been really fast progress in multiple platforms along different directions. The neutral atoms have emerged very recently as special because of this ability to scale them up and control huge numbers of them at the same time. But superconducting systems are continuing to improve quite quickly as well. I continue to collaborate with Amazon, working on superconducting circuits there. I think it's very hard to say in like 15 years what will be the winner. There are major challenges in all of these platforms. So I'm going to cop out and not really give like a more specific answer than that. Yeah.
If neutral atoms are beneficial because you can put them closer together and they don't interact as much, what's the benefit of ions?
Ions. So ions are very much like atoms in many ways, in the sense that they're all identical. They're all, they all have exactly the same structure. They're levitated in vacuum, not using optical tweezers, but using electrodes that can control the ions through their electric charge. They have a challenge, which is that they push on each other. But actually, this challenge is a double-edged sword. So on the one hand, it does make it a little harder to pack huge numbers of ions together. But it's actually a better mechanism than these Rydberg states to entangle the ions. So people can use the Coulomb force between ions to do higher fidelity gates. In fact, the new world record was just set like last week by a trapped ion group that did 99.99% gate fidelity for entangling atoms, for entangling ions. Neutral atoms, these Rydberg states are not quite as good. They're a little bit like more messy. These Rydberg states, you try to excite the atom, it will actually decay, and that can cause errors. So the record is like more than 10 times worse in terms of gate error rate. So I think that's really the pitch for ions, is that people have the best fidelity control over them of any system.
Yeah, why do you choose to use Vivium versus like SHA-2? Like what goes into that decision?
Why did you suggest strontium as an alternative?
You mentioned that.
Oh, did I?
Yeah,
I see. Okay, I thought that was a leading question. So there's a bunch of different atomic species that have been. So basically, what you need for this is an atom that has been laser cooled. Laser cooling atoms is easy for some atomic species and hard for most atomic species. The species that are easy to laser cool are species that have simple structure. And what I mean by that is, so the easiest species are the ones in the left column of the periodic table, which is the alkali metals. Those are easy because they have a ton of electrons, but most of the electrons are in filled shells. And those filled shells of electrons around the nucleus don't do anything. So you end up just having one valence electron that is really the relevant thing that causes all the structure. So like all of these energy levels, those are all different states of the valence electron. And that's pretty simple. So they all act like hydrogen because hydrogen just has one valence electron. That structure is very amenable to laser cooling. As long as the wavelengths are good for like good colors that you can make with laser set, those are the easiest types of atoms to laser cool. So rubidium and cesium are two that have been laser cooled for the longest, for several decades now. So they're the most mature in terms of like, you go out and you buy the right laser and you can laser cool the atom, no problem. Some newer atoms that people have started laser cooling are atoms with more complex structure. Strontium is one example. Strontium has two valence electrons. Two valence electrons already makes things a lot more complicated because these two electrons interact very strongly with each other. They form singlet and triplet states, different combinations of their wave functions. That makes them harder to work with in certain ways, but really special in other ways. So the world's best clocks, for example, are made out of a very, very specific transition between these two states in strontium. So a little harder to work with, but more complex structure. That can be a double-edged sword, but for some people, they think that's really useful for quantum computing. Another atom that recently people have really started to like is a terbium. A terbium also has two valence electrons, plus a nuclear spin. So there's like a bit different grab bag for each atomic species. One thing I'll say is there's always like a really fun effort of people trying to laser cool new atoms that have never been laser cooled. So at Berkeley, people just laser cooled titanium for the first time ever. And that is really cool. And maybe now in 5 years, you'll see a bunch of talks like this, but they're using titanium atoms. And titanium has even more complex structure, so it's harder to use. But if you figure out how to do it, or someone else like paved the way, then maybe that will have some really cool new features that you could use for quantum computing too.
How is your, sorry, I didn't quite word it well, but how is your research in quantum computing impacted by politics? Like I know like there might be some areas that are like less funded than others, and the California governor happened to just come by UC Berkeley and said, "Let's do this," sure. So it's kind of relevant right now.
Yeah.
And you said that you were in Amazon and like they're sitting aside like billions for like to host some a software something, right? And like what aspects are funded more, or what are like, I don't know if that makes
Yeah.
sense.
I should probably be clear that I didn't put a number on how much Amazon has spent, which I'm sure I would not be allowed to do. But collectively, the industry has spent billions of dollars, at least, on quantum computing. And so in a way, it is seen as high priority in the current political environment. And that's because it's this emerging technology. It has a bunch of applications, some of which are very well known and have very specific impacts, others less well known. The one that is most well known and why it has some political urgency is one of the applications of quantum computers that is known is that quantum computers can efficiently factor large numbers. Sounds like a very random math problem, but that is the basis of modern cryptography. So if you could factor really large numbers, you could break modern cryptography. that's seen as extremely important. It obviously is extremely important. There's always a question of on what timeline will quantum computers be big enough and good enough to do something useful in that regard. And but that is like one of the example applications that is seen as super high priority, super valuable, and important to be like aware of when that transition point will occur. So that has helped to make quantum computing top of mind for governments. And it's also just like a totally new technology. Many people are optimistic, myself included, that these will be like amazing tools for new scientific research to answer questions about physics that nobody's been able to answer before by like modeling physical systems that are too complex to understand in other ways. So it's generally seen as just like the totally new branch of technology, and it's getting a lot of appropriate support in my view, but I work in the field.
Relation with like the emergence of AI has like boomed all of a sudden.
I think for the most part, it's been a parallel emergence, at least to my knowledge. So like, I don't think the advent of like the recent advances in quantum computing are from AI at all. I think they've emerged in parallel. There's a question of can they fit together in some special way? And there are some people who have ideas about if quantum computers could help large language models do certain tasks more efficiently. There's a massive crisis in terms of energy consumption of AI that maybe some of you are familiar with. And that is probably going to continue for a while because the demands will continue to grow. And so, for example, some people think maybe quantum computers could be more efficient for helping AI do computations. Maybe AI can help quantum computers be more successful too. I think probably many people would think that there's mutual benefit. But at least for now, I would say like the recent emergence in the last 5 years have been pretty parallel, to my knowledge. Was there a question here?
What kind of skills or subjects would one have to be knowledgeable in to be able to start contributing to this kind of research?
So I think experimental, so it's a little bit easier, I think, in an experimental lab because you don't need to like have a super detailed understanding of quantum computing to work in an atomic physics lab or a quantum computing lab. Usually the tasks that happen in those labs are pretty discrete. Align this laser, stabilize this laser in a certain way. So you need to like, those are technical skills. In many cases, in many research labs, you would learn them on the job. And so you would hopefully have someone instructing you, like, here is the proper strategy for stabilizing this laser in like a really robust way, and also how to be safe while doing it. I think coding skills are super important. I would say like all atomic physics, all quantum computing labs, probably like almost all physics labs, coding is some important part of it. Like you take data by like programming your electronics, you analyze your data with Python. That's super important. So maybe that would be like one unifying skill set that I think is super useful to have.
All right. For time's sake, let's thank our speaker one last time. And I'm sure if you have time, you could say a couple minutes.
Yeah, I'll stay around for a couple minutes. Yeah, sounds good.
All right, thank you.